Thank you. So I've been doing auditory modeling and signal processing and auditory perception stuff for about 30 years, and I've never really interacted with the audiology field, so I'm very happy to be here to be learning what you guys are learning and to see how you approach the world. In some sense, you guys help humans hear better, and my job is to help computers hear better, and so that's what we're trying to do. I've also heard you guys have been working really hard for the last day and a half, and I'm sort of the oddball in this speaker lineup. So maybe you'll think of me as a chocolate cake at the end of your session. So a lot of what we're doing is motivated by these new interface paradigms for computers, and I suspect a lot of you have heard about these, the Amazon device and the Google device. And I wanted to just do a quick demo to show how well they work. Before I do that, though, how many people have one of these things at home? 10%? 5%? So it's good I come to things like this because I live in Silicon Valley, and Silicon Valley is very warped. So I've got 3 at home. But I wanted to show you how well they worked, and hopefully it'll work for this. Hey, Google, is there a good Mexican restaurant in Telluride?
You've got some choices. La Cocina de Luz is rated 4.4 stars by 79 people. People describe it as modern Mexican eats with a healthy focus. Do you want this result?
Hey Google, what time is it open?
I found a few choices.
Oh, okay.
Esperanza's Tequila Restaurant is rated 4.6 stars by 14.
Let's just go with my mic and leave this off. So it's a changing world, and one evidence for this is that when this was announced, let me turn this off. One evidence for this is when Google first announced this, a stock analyst said, but how are you going to show advertising on it? Because the stock analysts were worried. It's like, these devices can become so popular, could become so popular, that there'd be no way to show advertising for Google to survive. And I don't think Google had a very good answer. But anyway, these things are coming, and it's really important that we know how to make them work. And for me, it's one of the things that drives what we do, because we want these things to be in our houses, to interact with each other. We want to be able to interact with them just as we do anything else in the house, like our kids or our parents or whatever else is going on. So we want these things to be very natural. Another thing driving our research is the self-driving cars. The self-driving car people do lots of things really well, but they also want to be able to know when there's a siren in the background. So, we all, hear an ambulance and can do the right thing, and a self-driving car has to do the same thing. And it's a challenging problem because you've got this, microphone, moving through the air at 55 miles an hour, and you still want to be able to hear an ambulance around the corner. And so that's been pushing a lot of things. And I'm going to talk about a lot of things, but one of the things that we're actually shipping is some stuff we've been doing on automatically closed captioning videos from YouTube. And it's easy to do that with speech recognition, and some of the technology I'm talking about today is being used to recognize non-speech sounds. And so things like music and cheering, and I forget what else they're actually running in production right now. And so the technology I'm talking about extends from things like this that are actually already being used every day in industry, in the phones, in devices you have at home, and then stuff that's very, very, very blue sky. So this is the outline I want to talk about. Mark encouraged me to make this as short as possible so there's time for questions. So I've been throwing out slides all day long. Every one of these topics, there's at least 6 papers that goes into great depth. And at the end, I can answer more questions. Answer questions about what's, if you have any questions about these things. I want to talk about things that we've done with auditory models for hot word detection. Some things that have been happening for document search using these auditory images we've worked with. Some stuff we've been doing on recognizing sounds in the world, like the sirens I talked about before and the applause. And then the more blue sky stuff is how we're using attention and how people use attention and how computers can use attention to improve these interactions. So the very simplest thing is some work I did in a past lifetime on using eye gaze to improve speech recognition. And then the really blue sky stuff is we're actually starting to look at using EEG signals to control a hearing aid. So that works, but it's going to be a long time before it ships commercially, and perhaps not by Google, but it's certainly part of the research environment. So I want to talk a little bit about auditory modeling, which I suspect all of you guys know about, and tell you a little bit about our philosophy to it and what drives our interest in our products. We always start with sound, and we have a very simple auditory periphery model that we've been using. I work with Dick Lyon, who's been doing this longer than I have, and he has a new book out that talks about his modeling approach. So it's just a very simple cochlear model, but includes a lot of nonlinear effects, which we think are important, especially in real life situations. So for very simple things with very narrow dynamic range of sounds, linear models work really well. But we exist in a world with 80, 90 dB of signal noise ratio or signal level differences. And the auditory system can adapt to that, and we need our machines to do that. So we model all that kind of stuff. We spent a lot of time looking at something called an auditory image, which helps get the fine time structure for us, which we think is really important in the cocktail party effect and things like that, realistic auditory environments. There's some application-dependent feature extraction where we, depending on what we're trying to do, we'll look at different kinds of features because all this is being driven by real needs and real pattern classification problems. The machine learning is what's driving all this, and so we spend a lot of time building machine learning applications. And what comes out at the end is some sort of meaning. It could be there's a baby crying now. There could be an ambulance here. It could be applause. It could be a flute playing. Whatever is going on, what is being needed. We do that. And these 4 steps exist in a continuum from things that are very close to biology, biomimicry, which we find is very important for realistic situations, to more abstract things like machine learning. So we're trying to model how humans do everything. But we do find it useful to model at the very lowest levels what we know about the cochlea and use that in the dynamics of the system. And at the very high level stuff, we're doing completely computer-based with no connection to humans in the way they do it. But that's what we have to do to get things done. And typically what happens is the lower levels are very stable. So the cochlear model has been fairly stable over the last couple decades. And then all the innovations happening at the very top level. And so, things I'm talking about this week at level 4 will be different next week. It's really moving that fast. And there's a little gray area at the very right-hand side showing that the machine learning is then going to be influenced in the feature extraction. So we're have this little feedback loop going on. Our front-end work starts with some sort of auditory model. Dick is a very big fan of this WKB approach for modeling the cochlea, and he spends a lot of time building models of the dynamics of the system and implements the filter as this cascade of filters. And the details aren't important, but I just wanted to give you a flavor for the kind of processing we're doing in order to make these things realistic and work in the real world. One of the issues that we have is, as I said before, dynamic range is very high, from 20 to 100 dB perhaps. And when you start having these guys out in the real world, where someone was complaining yesterday that, their device can recognize what they're saying from the other room or from upstairs. So they really are trying to make this work over long distances. And the typical way that engineers deal with sound is they compute a log of it. And the log is a great thing because it compresses things into a much smaller range of numbers. But the problem with the log is that left-hand side goes down to infinity, or negative infinity, I should say. It's not a very stable operation. But that's what the engineering side tells you to do. And what our group has been looking at is implementing a soft compressor, much like what you would see in a hearing aid, or what the inner hair cells might do, and using that to process the sound before we do recognition. So this particular algorithm is called PSEN in our group. It means per channel energy normalization. And there's only 3 equations in this talk, so I just want to give you a sense again. The basic idea is you've got this energy term, and you want to smooth it by dividing by or you want to normalize it by smoothing it or dividing by the smooth energy. So if the average energy is like this, and you've got these peaks going above it, then you want to represent that. And if the energy is going below the average, then you want to also represent that as a negative number in this case. And so we have this simple energy normalization filter here. Oops, I'm sorry. That has a couple of scaling constants in it. And this forms a very important front end for our hot word detection. So these devices have a microphone that's always on. But we don't want to recognize everything that's being said. One, for computational reasons, two, for privacy reasons. So these devices all have a hot word, or whatever. I don't know what Amazon calls theirs. But this device is looking for the words, OK Google or Hey Google. And that has to be recognized on this device with very low power and very small computational effort before the microphone gets turned on, and then the speech gets sent to the cloud for the actual real work. So before, when I asked, is there a Mexican restaurant in Telluride, that was being done, the microphone, it was sending it to the cloud, recognition was being done, it was in a search query, just like you would type normally, and the result was coming back, and then it was being synthesized here. The first step in all this is the hardware detection, which you want to be reliable, you want it to work no matter what else is going on. If there's TV blaring or the radio or the kids are playing, if you say, OK, Google, it's supposed to respond. And that processing, that step, is going through this kind of algorithm. This is, it's hard to tell what's going on in this case, but what we really want to do is we want to spend more of the signal processing, more of the numbers that we're getting back with the parts of the speech that are most important. So we really don't care about the silence. Silence is silence no matter what's going on. If it's silence, we want to ignore it. And we really want to spend all our time looking at the formants and everything else that's going on, the fricatives, trying to make sure we represent that information really well so that the machine learning operations have the best opportunity to do what they're doing. And then, since we're at Google, we specialize in machine learning, so these parameters that are circled in red here, we can actually learn. And so we had lots and lots of recordings of people saying, OK, Google, Hey, Google, in all sorts of environments. And we can measure our recognition accuracy as a function of these parameters. And so we did those tests, and I don't know what the numbers are, but that's what's actually in this device here and all the other devices we do, is this kind of normalization. And we're very happy with this because the auditory world, the auditory perception world, taught us how to do these kind of normalizations so we can put them in the box. And that's what justifies our group's existence at Google, is things like this. So that's sort of the simplest operation we can do. We're looking for the right kind of representations for a lot of this stuff. And what Dick and I have been looking at for many years are these things called auditory images. Everybody talks about the frequency axis. Everybody knows that frequencies get mapped into the brain. And there's a tonotopic axis, and you can lay it out, and it's monotonic, and all that kind of stuff is good. But that really doesn't tell the whole story. So cortex is a two-dimensional object. So one axis is definitely tonotopy, or frequency. What the heck is the other axis doing? We like to think of this as an image processing problem. So what we write are these things called auditory images, which are based on this idea that the auditory nerve carries a lot of information on the signal. And this is, I actually don't know, I assume this is Bertrand's figure, showing time along the bottom axis, a horizontal axis, and different frequency channels along the vertical axis. And often when we talk about a spectrogram, when we talk about a spectrogram, what we're saying is at 2 kilohertz, there's 150 firings a second, or whatever it is. There's some amplitude for that. But the real signal is much more complicated than that. And so in this particular signal, you can see a volley of firings here around 5 milliseconds. And then there's another volley of firings around 15 milliseconds. And so this is a really good indication that the glottis is opening and closing at a 10 millisecond interval, which corresponds to about 100 hertz pitch. And this is the information we think that allows our brains to understand sounds in a very complicated environment. So if you have a single sound, if it's a very quiet thing and only one person is speaking, a rate profile, a spectrogram, tells you everything you need to know about what's going on to be able to recognize the speech. But we don't want to work in an environment where there's only one person speaking. We want to work where there's road noise outside and multiple people are speaking and all that kind of stuff. And so we've been spending a lot of time looking at how do we get this information, how is it represented, and what do we do with it. Our favorite representation is John Licklider's duplex theory of pitch perception. And he has this unified representation of sound that represents frequency on one axis. I guess it's on the horizontal axis for here. And then the other axis is representing a time delay or correlation lag. And there's various ways of implementing it. My favorite way is with a correlation calculation. Roy Patterson, who was at Cambridge, has a similar computation. He calls it the stabilized auditory image. But the idea for these representations is to represent both the frequency information and represent the fine time scale. And there's various ways of computing it, and I just want to give you an example of how I compute it. This is from a video I made many years ago when I was at Apple. We had a demonstration for the executives at Apple about our work. Dick and I were working together at Apple then. And we had Leonardo da Vinci as an actor, an opera singer, come in and illustrate the various technologies the research group did. And so he narrated our display. So this is Leonardo da Vinci introducing the parallelogram. And I lost my mouse. Okay, there it is. Where's my mouse? There.
Sight is the lord of astronomy, the prince of mathematics. It counsels and corrects all the arts of mankind. What fun. Here, observe. See? The dark vertical lines follow what the muscles in my throat do. Now, I will change the shape of my mouth, but keep the same pitch with my throat. Yes, yes. The horizontal lines determine what sounds come out of my mouth. Fascinating. If I had such a machine, I could tell who it is that was speaking by the vertical pitch and what was said by the horizontal lines.
So that's just one of many ways of capturing this information. It's one we've been very successful with. I've used it in modeling pitch perception. A lot of people argue about this. It's a very, very successful model in lots of ways. And it formed the basis of some work that we did on search and in copyright detection by segmenting it, doing some sparse coding, and then converting that into a feature that we call the document feature. And that got used in lots and lots of different kinds of work. The first thing was some audio document search where you want to say, here's a sound snippet, find me other sound snippets just like this. And so you can use this representation for that. It was used in in the first YouTube copyright detection problems. So people upload video to us all the time, and we get in really big trouble with the record labels if our users are uploading, copyrighted songs. And so it's important for us to be able to find them and then negotiate with the user to have the right thing happen. One of those things that can happen is we can actually remove the song from a video. So there's YouTube song eraser at one point. I'm not sure if it's still there. Where if there was a copyrighted song in the background, we could remove it so that way the video could be put up for the public to consume, and various other things. So more recently, we've been building a real-world audio classification system. We call it AudioSet, and it's based on this idea that it's based on technology that came out of the image processing world. So the image processing world has been spending a couple decades building object classifiers, and the output you get from these things is what's shown here on the left figure, where these networks or these computational systems can look at an image and say, okay, there's a dog in that red box, and then there's a person in a chair, and whatever else is going on there. And this is all based on an image database called ImageNet that was been put out by Stanford. And speech recognition has been solving a similar problem by looking at the spectrogram in various ways, building these very deep neural networks, multiple layers, and then using that for doing speech recognition. And so I'm pretty sure every single phone out there is doing exactly what's on the right-hand side here. Apple, Amazon, Google all have the same kind of technologies, and I'm pretty sure we're all doing it with a deep neural network. So that's all fairly easy. There's all sorts of things we'd like to do if we had access to the audio events, so we could tell what audience are there, so we could do content-based audio search. You could say, okay, give me all the goat sounds you have. In surveillance applications, Nest would dearly love to know for their customers when the dog is barking or when the baby's crying, because that's useful for the users. And we want to be able to use that for all sorts of devices who care about the environment, like cars and things like that. The way we do these sort of things is we have a fairly large collection of video that has been sent to us called YouTube. And a lot of it includes audio. And a lot of it's labeled with various things. So it might be labeled birthday party or cat or water skiing show. And we can use that information to build a classifier. So we're taking the data and whatever labels people give us, which might not necessarily correspond to what the sounds are, and put that into these computational algorithms that I'll talk about. And then what comes out is an audio event classifier, and I guess awesome was one of my engineering friends' description of it. So I'll let you decide if it's awesome or not. There's various ways of solving this problem. The videos come in with some length of video, so it could be anywhere from 10 seconds to 10 hours of video, and some sort of labels or some sort of title that came from the user. So we might have a 3-minute video that says Bagpipes Scotland song, and that's all information we have. And then we ought to be able to figure out what that means. That's the whole soundtrack. Shorter term, we're going to look at things like events. So we want to be able to say, okay, this 10 seconds corresponds to the bagpipes, and be able to classify where the bagpipes are in this video. And then at a finer scale, we want to be able to say things like, okay, here's speech, here's bagpipes, here's tap dancing, and identify all the content in the video. So we're not there yet, but we've made a pretty good step at this. We do have some data. This particular experiment that I'm going to talk about was done with 100 million videos that we have, all with labels of various sorts. And this corresponds to 600 years of audio, if you laid it all out, 20 billion input examples. And we had a bunch of different kinds of labels. So this is 30,000 class classifier. And some of the things are obvious, like song and music and game and sports. And some are less obvious, things like custom motorcycle, which you can imagine has a sound, and retaining wall. And I have no idea what that sound is. But that's what we get. That's what people give us, and we have to work with that. On average, we get like 3 labels per video, so we're not getting a lot of information. But luckily, we have a lot of videos, and so we can learn something still. The way we do that is we take the audio that we're getting in, and we convert it into a spectrogram, and then we take 960 milliseconds, and there's a reason for this based on the architecture, but it's essentially arbitrary. 960 milliseconds of spectrogram, so frequency along axis, time along the other axis, and that becomes a patch that we can then apply to our network and learn and classify. Is this a cat or is this hip-hop music? And that's what we're going to do. And this is showing some animated cartoons where we got some frequency glides, and I don't know what the dance music is looking like. There are innumerable architectures and computational reasons or ways of doing this. I just wanted to give you a flavor of what's going on now, because this is really the hot stuff in machine learning. This is what people are doing now. There's a meeting next week in Long Beach called NIPS, where I think they had to cap registration at 6,000 people. And it's all going to be about stuff like this. What goes in is that 64 by 96, 64 channels by 96 frames, 960 milliseconds, spectrogram slice. And the very simplest architectures is what's called fully connected, where I don't know what 64 times 96 is, about 6,000 weights. So you have 6,000 things coming in. Fully connected means that you multiply everything by everything else, and you get 6,000 layers, 6,000 outputs coming out. And you keep doing this, and at the very end, you have to decide which of the 30,000 classes this is. So the last layer is going to be 6,000 inputs by 30,000 outputs. So if you remember your math, this is a 6,000 by 30,000 dimensional matrix. But if you add all that up, that comes to 11.2 million parameters. And I'm guessing that's a few more than what a hearing aid has. But that's sort of the simplest baseline for all this stuff. People have been iterating this over the years, and here's another one that has what we call convolutional networks. And this raises the number of parameters up to 767 million parameters. So again, this is fairly small for us. The next one that was actually useful for us was this thing called the VGG network. This was just invented 2 years ago and is in widespread use. And now we're up to 2.4 billion parameters. And it's got all these layers. So all these layers are why it's called a deep neural network. Each layer is doing one kind of computation, a matrix multiply or a convolution or something like that. The image processing people have been going nuts and doing all these very complicated things. Inception and ResNet, I think, are the basis of the photo recognition that goes on in these phones. So if you've been taking pictures on an Android phone and uploading them, you can actually type a search for some obscure word, and it'll find those photos that have that. And that computation is being done with a network that looks like this, where you have anywhere from 4 to 2 billion parameters being applied to an image, and then a label comes out saying, okay, this is a retaining wall, or this is a cat. And we can do these things fairly quickly, and it's obviously easier in the cloud, but a lot of this stuff can happen on the phone now. These are the kind of results we get. Performance for these kind of problems tends to go up with complexity of the network and how much data you have. And so you can see here these bigger networks on the right-hand side start getting a pretty good performance, where we're getting 16% correct, 16% correct, and 18% correct on this very, very difficult task. And so that's encouraging. We can also look at our performance as a function of training videos. And so I said we started with 70 million videos, but it turns out we get pretty good convergence to the right answer with 700,000 videos. And what this tells people like me and people that work in the industry is like, oh, we can go crazy with a network because we still have 100 times more data than we need. And so, we can just say, okay, let's make the network more complicated, more crazy, and that'll improve our performance. And that's typically what's happening is as you add more data, you get better performance. The kind of things we look at are performance as a function. We look at our performance in lots of ways. This is one way which we thought was interesting. On the bottom is class probability. So we have a wide range of videos. We have lots and lots of cat videos, and we have very few videos of retaining walls. And so that's what's on the horizontal axis, and -1 corresponds to a prior of 10%. So minus log of 1/10 is -1, and -6 is 1 in a million videos. And we thought it was really interesting that the mean performance was pretty much constant, no matter how frequent it was. So we were kind of expecting things like cats would be really easy to identify, and it would perform really well. But we do equally well on cats as we do on retaining walls. And so that's the kind of things we look at. We've actually released a smaller data set called AudioSet. So it's on the web. It's 2 million 10-second excerpts. And we've had each of the 2 million videos human annotated. So a human has looked at each one of those videos and said, this is really a cat video, this is really a didgeridoo, this is really a hyena, or whatever else is going on. And we have a bunch of test data. So if you're interested in this kind of problem, if you have students interested in this kind of problem, there's a data set out there that's all free, and it's very useful. And this is the kind of results we get. It's a little hard to interpret because it goes by very fast. But again, you can see what sort of things we're looking at. A pen clicking. So you can see it's picking up the dog. I'm not sure what it's keying on. A lot of silence here. I guess it's the breath. You can't really hear it in this environment. Whistle. Theremin is a musical instrument that sounds a lot like a whistle. Bell. Okay, you get the idea. So this is the kind of thing that's actually being done in our lab, and we're actively working with our product groups trying to figure out how we can help them do things like this. I want to talk a little bit about some work I did at Microsoft on understanding attention for building better speech recognition systems. So I like to show this example. This is Bill Gaver, a number of years ago, built a system called Sonic Finder, and I'll play you a few seconds of it. He was trying to build better interfaces using sound to help the user's interactions with computers. This is very old, you can tell.
My name is Bill Gaver, and this is the Sonic Finder, which is a prototype auditory interface that I developed. And in this interface, many of the events are associated with sound as well as graphical feedback. So I can select files, drag them around, open windows, and so forth. At this point, I'd like to show you in more detail what the Sonic Finder does. Selecting objects in the Sonic Finder makes sounds, and those sounds depend on the type of objects, so that folders make one sort of sounds, applications a second, files a third, and disks yet another sound. The sounds also depend on the object's size, so that small objects, like this small folder, make higher sounds than large objects, like this large folder.
Okay, you get the idea. This is done a long time ago, before Facebook, before Twitter, all that kind of stuff. This went around Apple in a day. I mean, it spread like wildfire. It was really, really popular. People loved it for 5 minutes. And the reason that people loved it is because it's really nice to have feedback. You want your keyboards to give you a little physical feedback when you press a key. And it's really kind of nice to know that when you do something, it's going to give you a little feedback. So if you're distracted or something, your perceptual system, your auditory system can say, oh yeah, it really happened. But the bad news is that it was really, really hard for Bill to set the right level. I mean, there was no feedback on the auditory environment. So he's playing these sounds. And if you set them at the wrong level, if it was too low, it didn't matter. If you set it too high, every time you're doing something, the system's blaring at you saying, pay attention to me. And it's really hard to get work done when your computer keeps saying, pay attention to me. And so if Bill could have understood attention, Bill's very smart, he understands attention. If Bill could have actually modeled attention, modeled what people were doing, modeled the environment, he could have played the sounds at the right level so that it was audible, but not so high that it actually pulled you away from your task. And we've been doing a lot of work on saliency, which I'm not talking about today. But the attention process and saliency is really important for these new user interfaces. We really want the machines to be able to do the right thing for us. And part of that is knowing what level to be at. Just like when you talk to your friends, they know how loud or soft to make some sound they're going to use to attract you or get your attention. We spent a bunch of time looking at eye gaze information for automatic speech recognition. Before I explain this experiment, I'll tell you about the pilot experiment. We had a graduate student from CMU helping us that summer. And we wanted to set up this experiment where people had to either point or look at the screen and talk to it. So the idea was that there's a screen, and you're going to talk to it. It's like, hey computer, what's the temperature in Telluride? And to do that, we set up this Wizard of Oz experiment where the user sat in front of the screen. There was a wizard behind the curtain who was controlling the computer, and he was listening to what the user said and carrying out an action. And the user was trying to do things like find an obscure form on the Department of Motor Vehicles website, or buy some shoes, or find out time of a concert. And what was interesting is that the wizard also had access to the eye gaze information. So we had an eye gaze tracker. The subject was looking at the web pages, trying to figure out what to do next, looking at the screen, and then giving commands to the computer or to the wizard. The wizard knew what the person was going to say before they said it, just based on the eye gaze information. It was cheating a little bit in the sense that the wizard knew where things were going and what to look for. But the eye gaze information was really like a window into the soul, window into the person's thought process, and that really can help the speech recognition process. And so this is an experiment we did where we just had people read some text off the screen at random, and we would try to build a recognizer that would recognize that speech as well as it could. And so this is some eye tracking data as they're reading the New York Times web page. And the things we were looking at was how do time and the spotlight, if you will, affect your perception. So in order to see something, you've got to foveate on it, roughly speaking, and that's what you're going to be able to say. And so in this case, they were picking out a sentence, starting to read it, and before they were halfway through the sentence, they were already off looking somewhere else. And so it's a fairly complicated process, but we do it all the time, and we're trying to build computers to model all this and improve our recognition system. The way we would do this is to build an automatic speech recognition system, ASR, that has a language model. And what makes speech recognition work is language models, which says, these are the words that are possible in English. These are the words that follow each other. You know that we're talking about audiology here, and it's very unlikely I'm going to say the word elephant. But if it was a noisy environment, you'd probably miss the word elephant because it wasn't part of your audiology language model. And so that's built into the system. The way we actually implemented it was we had this generic language model, and then we had a page-specific language model. So this was all the words on the page. And then we took the recognition results from that, and then we rescored it, it's called, where we add the gaze information and say, okay, you told me what you think it is based on the audio and the language model. Now let's include the eye gaze information and see how that changes. And what comes out at that first stage is this thing called a lattice. And so the system has said, well, based on the audio, it's this path. But maybe based on whether we're looking on the screen, this is kind of a silly example, but maybe the recognition should have been looking at the word guest, because they've been looking at something about guest services or something. And so the eye gaze can then bias the system to do a better thing. The way that we've talked about complexity in speech recognition systems is perplexity. Perplexity is the average branching factor of the grammar, the language model. So if you have a phone number language model where all you can do is recognize phone numbers, perplexity is essentially 10, because any digit it can be followed by 10 other digits. But real language is much more complicated than that. And we had a very generic language model, had very little information about English, just a lot of words, and had a perplexity of 1,000. And then we were going to start improving that by adding other information. So when we added the page model, so the generic language model plus the page model, that got us to a perplexity of 26. So this is our real baseline. And then when we added the gaze information, that cut the perplexity to 15. So we got almost a factor of 2 improvement in the perplexity, or a factor of 2 reduction in complexity by adding the eye gaze information in this thing. And factors of 2 are really nice because those are significant. That gets product managers' attention. And so that's a useful thing. We demonstrated this by building a system that would recognize ambiguous sentences. And the classic ambiguous sentence in English is the words recognize speech, as in, you're out on the beach, or recognize speech. So they have very similar phonemes, and I built a system that would recognize these things and use the eye gaze information. And what you're seeing is a summary screen where I was very careful to say recognize speech. And so the acoustic result was supposed to be recognize speech, what's shown in the blue highlight. But then when it's rescored, it's using the eye gaze information. So the whole time I'm saying recognize speech, I'm actually looking at the top box. And you can change the priority of these things, but in this case, for purposes of demonstration, I wanted to make sure it was biased toward the visual case. I looked at the Microsoft homepage at one point. I think there was like 12 different places where they mentioned Microsoft Office, but every single one of them meant something else. So one case it was support plans, one case was buying it, another case was using it. And so even though the exact words were the same, we want to do different actions based on what they're looking at. And so that's that kind of thing. Here's a quick demo of what this looked like. I can find my mouse here. So I'm looking up there in the upper right,
Speech.
and I said the bottom one, and that was the result I just showed you. Now I'm going to look
Recognize Beach.
the bottom one, say the upper one, and we get the opposite case.
Microsoft Office.
In that case, it's the same either way. Anyway, you get the idea. So a lot of what I'm doing now is looking at things like attention. Many years ago, I was at a binaural meeting. So all the best people in the world that do binaural hearing were there. This is at Wright-Patterson. And there was vigorous discussions. And I swear, after every single talk, someone would ask a hard question, and we talk about it for a minute, and then finally someone would stand up and say, we can't do that, that's the C word, where C meant either cognition or cortex. And we were all peripheral people. We're engineers, we're very low-level binaural perception people, and so we all laughed and said, yep, no problem, we're not going to deal with cortex, so we're going to ignore that. That was 20 years ago. Now we have to. A lot of the stuff that we want to do really depends on how we're perceiving the world, how humans are perceiving the world. And our machines are not just passive things. They're not hammers anymore. They actually want to interact with us. We want to interact with machines just like we do other people. And so having a model of attention and understanding attention is really important for the machines we're doing. I'm going to finish up with some stuff that I've been doing with a consortium in 2 places. One with this workshop in Telluride, Colorado that I work at. And that has then morphed into a European project called COCOHA that's trying to build a hearing aid that uses your brain waves, uses your EEG signals to tune its parameters. And I'll explain what we're doing, and then I'll tell you how realistic it is. So I don't know if you're familiar with EEG. EEG's had a long history. They're tending to a lot of the stuff that was done, or a lot of the things that have been done over the years, were done in very impoverished environments where they don't have a lot of data, they don't have a lot of computer algorithms to process the data, and so they do very simple things. And so a very classic experiment is to play people a sound, change it a little bit, and see how the EEG differs. And so they look at these things called ERPs and say, oh, there's a P300, it changed a little bit. That says that the brain noticed that, and that's something useful. And in practical situations, they can turn that thing into a brain-computer interface and say, okay, this person's locked in, he can't do anything, but he can think things. And so maybe you play him a dog, or you show some characters on a screen, record the EEG signal, and then we can build detectors that say, okay, this person is looking at a dog, or this person is looking at the letter A, or something like that. So that's what I call classic EEG, BCI type applications. We're looking at a little harder problem. We want to understand, what are you attending to? Are you attending to Joe, or are you attending to Betty? So the paradigm we have is we have a subject in the middle here, and it looks like it's hard to see on the screen. So there's a person here in headphones, and that person is listening to two different simultaneous speakers. And just to make it more interesting, they're both male speakers, and they're both saying these old-time stories. So 20,000 Leagues Under the Sea, Journey to the Center of the Earth, and we tell the user to pay attention to one or the other. And we do this diotic or diachotic, so either way. It's harder when it's diotic, so it's the same signal in both ears, but we can do it. They've been told what to do. We're measuring the EEG signals, and we're going to build a decoder that says, what is the connection between the EEG signal and the audio you're attending to? So we're trying to recognize speech from your EEG signals. But not just any speech, we're trying to recognize the speech you're attending to, because you're actually hearing both signals at once. So there's lots of reasons for doing this. I wear two caps. I'm very fortunate that I have two caps. I work in industry, I like industry, I get paid by industry, which is good. But I also have a scientific cap, and I work at Stanford, and I like the scientific questions. So the scientific question in all this is, what does attention look like in the brain? How is audio processed? What's going on there? There's lots of models. We want to tell with the EEG what's going on. MRI can't help us because it goes by too fast. EEG is a lousy signal, but at least it has high resolution and time. And the very rough model is, okay, the thing you're attending to, you're just attending to my voice, is going into your ears. It's obviously being represented at the auditory nerve, the cochlear nucleus, A1. It's going all the way up into your brain, and it's being processed to the full extent possible. So that's why the one ear goes all the way to the top. The signal you're not attending to, the person next to you that's breathing funny or whatever, goes partway into your brain, and we don't know what happens to it. But it definitely doesn't go all the way to the top. And it's a very complicated story, because if someone you're not listening to says your name, that's going to change your attention. Or if it's a loud sound, that'll change your attention. So we're trying to understand what that looks like. And we're going to get these signals out. And the EEG signal is going to be a sum of both the attended, the red signal, and the blue signal. So we're going to get both of those. And what we're going to do is do some denoising, and because EEG is very noisy, eye blinks and stuff like that screw us up, and try to build a decoder that decides what you're listening to. What you're attending to. And as part of that, we want to know what you're attending, what the signals look like. So the good news is we can do it. This was experiments we piloted at an elementary school in Telluride where this workshop happens. But then Ed Lawler, who's a colleague of ours who was working in Dublin at the time, actually had some data for this back in the lab. And we worked out how to analyze it in the workshop. He went back to Dublin and analyzed it. And these are the kind of results we're getting. So look at the top blue curve here. This is, sorry, the numbers are small. The numbers here go from 50 to 100%. And the blue curve is a sorted list of performance by subject. So the lowest performing subject got, 57% accuracy. But almost all the subjects got well above chance, and a whole bunch of subjects graded at 90, 100% accuracy. So this is pretty neat. With EEG signals, as flaky as they are, as noisy as they are, we can tell what you're attending to. Were you listening to 20 Leagues Under the Sea or something else? The other way to look at the data is how long does it take to make a decision? So in this case, we have from 0 to 40 seconds. And at the various, I'm not sure why this starts at 0. Anyway, with a few seconds of data, we can start making a decision about chance for the best subject, and other subjects took a little longer. And I was just back in Zurich this week working with these people, and obviously this is not published yet, but they were saying that they're getting good data for estimating these decisions in 4 to 8 seconds now. So we've optimized the algorithms. We've got better algorithms than we did this work back in 2015, and we do this really well. The other thing that makes this practical is we're also working with in-ear EEG signals. So, you know, it's kind of geeky to wear an EEG cap. It's probably not something you go around the world with, but we can put EEG sensors on the hearing aid in the ear canal, and we can get useful signals. So it's probably not going to be this level of performance, and we're still trying to characterize it. I think we've only got data from about 20 subjects, and some of them have graduated and gone away because they're all custom fit molds. But this is possible to do in the ear with some latency. We don't know what that'll be. And there is a demo existing of this back in Zurich and Denmark and Paris, where with an EEG cap and a decoder customized to the user, they can shift the hearing aid's amplitude to pay attention to the speaker over there or the speaker over there based on what you're attending to. And you can switch all that. So it's a pretty wonderful world. Lots of exciting things going on, lots of data, lots of need, and lots of need drives money and funding, so we get to do all this kind of fun work, and we've had a great time. So I have to acknowledge a whole bunch of people. Everywhere where I said I really meant we. There's a whole bunch of papers. A lot of the work I've been doing has been motivated and described and noodled over at this Telluride Neuromorphic Engineering Workshop, where we bring students and faculty together for 3 weeks of workshop, and we actually sit down and build things over the course of 3 weeks. So we have 18 days between Monday when we start and Friday when we demo to get something working, and a bunch of people who are shown there have helped with that. Brain Vision has been very generous and very kind, and every year I call them up and say please, and they send me $50,000 worth of EEG equipment. I've never met them. They're very nice to me, so I owe them a great thanks because we've trained a lot of people with their equipment and gotten really good results, and that's been a lot of fun. The work on attention that I started doing at Microsoft and speech recognition, so Dilek and Larry were very helpful. At Google, I primarily work with Dick Lyon, but there's a very large machine hearing group, maybe 20 people, who work on various things from text-to-speech to binaural and multi-microphone arrays to things like that. I've also been leading and organizing the Stanford Hearing Seminar for maybe 20 years now. And that's been a wonderful forum. If you're in the Bay Area, look for the Stanford Hearing Seminar online and join the mailing list. It's mostly aimed at post-PhD researchers in audio, and we have a really wonderful, vibrant environment, bringing people from all over the place. It's pretty rare. We actually had someone fly up from LA for one of our talks last week. But usually it's people from all over the Bay Area that come. And then a number of people like Brent Edwards, who's now at NAL, and Irv Hafter, who was at Berkeley, and Azim Kalini at Sony, help with data and thoughts and things like that. So we've been having lots of fun, and I thank you for your attention. And I'm happy to answer any questions.
I have a question. Well, actually, it's more of a comment. So have you heard about pupillometry?
Yeah,
right.
yeah.
So like when people are having a hard time processing, particularly speech and noise, their pupils dilate, right? And so we can measure this with our clinical tools. But you guys have Google Glass, right? Don't you have glasses?
But they don't have a backward pointing one.
Not yet.
I wish they did.
Not yet, but right. So because that might even be easier than EEG, right? Because you can tell if the person's stressed out or not, right? So if the hearing aid or whatever device is, like showing that the person's struggling, maybe they could switch to another program or,
Yeah.
Anyway.
Well, I mean, we also have cameras on these things that are pointing at the face, and we can actually do eye tracking with these. So we have a group that's building eye trackers for phones, and it's not as precise as the $100 eye trackers or the $50,000 ones, but there's information there. Yeah, so I've been working with Maria Chait at University College London on auditory saliency, and she's been looking at pupillometry as a way of measuring saliency. Why does this pop out? But we've been using Amazon Turk for collecting user data, and so yeah, I don't do it myself, but I work with people that do. I actually forget what questions I gave Mark for the continuing education thing. So if there's something I didn't cover, please ask, because I have no clue what I told Mark before.
Hi, thanks for your talk, Malcolm. Just a question on the last binaural study that you just did. Did your decoder have just a binary choice of following your EEG? And did the folks in Europe that you met with, do they have a more open set of data to look at what you're perceiving and
This
intention?
result's only a week old and already asking for more. So the way we actually do it is we actually build decoders that predict the audio. And so you can go either way. You can go from audio and predict the EEG, but that's very noisy because the EEG signal represents lots of other things that are going on, like your stomach grumbling, or someone walked by and whatever else is going on. So we actually get much better results if we take the EEG signal and try to predict the audio, the backward problem. So we build these decoders that go backwards, and there's lots of ways of doing it. And then what we actually do is we take the clean signals that we know we have from microphone array or from whatever else and say, okay, does the prediction match sound A or sound B? And so we're building these decoders followed by correlation that does that. And all the experiments we've done so far have been two-way. But yeah, obviously we want to do more. There must be some question I didn't answer from the...
I found your talk really interesting because I've always thought that, in certain cases, you'd be in a noisy place and you'd want to focus on a familiar voice, like if you're with a companion at a restaurant and there's speech all around. But in another case, like if you went to a party, you'd want to focus on the novel voice.
Right.
So listening to your talk seems like there's potential to develop some tools to accomplish that, between the categorization of sounds. You could have sounds that are weighted as being more familiar, and then you can also focus your attention with the EEG element. So it seems like the two combined, it seems like that has potential to help people at some point.
I took it out. We actually did an experiment like that. I don't know if I can find it quickly enough. Oh, here it is. This is Andy Oxenham in a cocktail party, and he was listening to two different speakers. And the cocktail party is sort of the prototypical really hard case, because you might be looking at the person giving you hors d'oeuvres and saying, listening to her say, these are wonderful, but you really listen to the person behind you who has a really good gossip. And that's what the cognition is doing. That's what you're trying to do. And so in an abstract sense, you're sampling all the conversations around, looking for the thing that's highest value. And so in your case, you sort of, I get the benefit of the doubt because I'm up here on the front, and so you're saying, well, maybe I'm the high value signal. But you might be listening to somebody else and trying to listen to somebody else. And so we modeled this. We wanted to model this. We actually built a system like this in Telluride, where we wanted to do this, but we didn't want to model all the complexity that human needs. And so we changed it into a digit recognition task, where we told the system, it needs to recognize the highest value things, and value is going to be based on numeric value. So that sort of abstracts away all the complexities of food and dating and everything else. And so, one person is saying a bunch of numbers, and the other guy is saying some other numbers, and we wanted to build a system that could, figure out what that was. And so, this is what we built. A binaural receiver in the middle, because Barbara Cunningham told us binaural onsets were really easy, and they weren't. But the key was there was these two signals. One was salience. So that's trying to say things like this are salient, or my voice is salient for various reasons. And then attention, which is a top-down thing saying, I really want to pay attention to you because you're what I'm supposed to pay attention to. And the cognition box, the C word, was trying to balance these two needs. And we built a system that actually implemented all this stuff and actually worked in 3 weeks. And it was very instructive. But it's this kind of model is what's needed. And maybe novelty is more important than familiarity. And so that would change your value function. And so that's how we think about it. Back in the back?
Yeah, I'll move back there. But can you touched on it really briefly, but maybe you could expand just a little bit. There's another question about the speech and noise.
Yeah.
So about, and I think you said about YouTube and removing. Can you just expand a little bit, like about categorizing sound and erasing unwanted noise?
So I'm an engineer by training, and I play with the science of perception. I really like the science of perception. And to answer Mark's question, I put my engineering cap on. So we have no clue how the brain recognizes sounds. I mean, we sort of have a clue about bird songs and birds, but we'd really like to be able to know more about how we classify sounds. And so to answer Mark's question, we turn it into an engineering problem. In that case, all we care about is how well do we do the task, what percentage accuracy do we get, and that sort of thing. And so we're building these very deep, wide recognizers that look at the sounds and say, oh, that's a bird, that's a cow, that's a flute, that's a bass guitar, whatever else. And we're doing that with all the noise that's on the system. So it's actually kind of interesting. We had a labeling problem when we started this where we got a little bit of video that was labeled cat. And we handed this to a human annotator. And the human annotator could not find the cat. And it was there if you turned up the volume really well, but it was down there so low. And so that got labeled cat, and our system's going to try to identify that as a cat sound. So it's going to be superhuman performance looking at meows in the noise, and we can do that. Did that answer your question?
Oh, is this going to be applicable, do you think, to cochlear implants, for example?
I hope so.
Yeah.
I have no clue how.
Okay.
As someone who spends a lot of time looking at fine time structure in the chorogram and stabilized auditory image, the information's there, and I don't understand how the cochlear implants are using fine time structure and how the brain processes what they give it. So yes, there's hope. On a more practical level, we're actually working with deaf people to try to take our sound representations and turn them into something that deaf people can use. So in a sense, that's a retinal implant. But yeah, we want to do that. How it's going to work with cochlear implants, I don't know. That's a really, really hard problem.
I remember several years ago talking with engineers about automatic speech recognition and so on, and when I looked at the performance of their systems, they looked very much like people with hearing loss, making the same kinds of errors.
You're very generous.
Do you envision a situation in which you might be able to take speech in noise, identify the speech, and then resynthesize it as a system that's free of noise for the person to listen to?
Well, there's lots of ways of answering that question. Speech recognition has gotten a lot better in the last few years by converting to these deep neural networks. And it's really, really robust. It's really quite surprising how good it is. One answer to your question is there's a lot of people looking at building speech enhancement systems that look at things like a spectrogram and say, okay, this is where the speech is. We're going to subtract everything else out. And those have gotten a lot better in the last few years. So that's one way of doing it. I would really love to build a system that would do really well at English and would completely fail at German. And so, a lot of what my colleagues want to do is they want to do it independent of language, independent of person. But I think it would be, for training, or I think for illustration purposes, it would be really cool if it could clean up English. It knew English really well. It knew things like ba and ka and all that kind of things that were in English, and completely screwed up on German. And we're starting to see those kind of levels of performance.
Yeah, but the big challenge, of course, for the people who work in the hearing aid engineering business is you've got 10 milliseconds to do this, to do all of this. Because if you're lip reading and hearing, they can't be 40 milliseconds apart.
Right. 960 milliseconds is a long time. I don't know what the answer to that is. Speech recognition needs a little bit of context in order to make its decision. It's far from perfect. And yeah, latency is an issue. We do have some speech enhancement systems that are low latency, but they don't perform as well as speech systems that look at both sides. And it'll come.
Thank you very much.
Thank you.